Thank you very much for the kind introduction. My name is Axel Schönbeck, and I am CEO and co-founder of Neue Labs. At Neue Labs, we build lasers. And I think we already heard in the previous panel that lasers are a very important part of today's technology. And actually, we basically use lasers in our everyday life, for example, when giving presentations. Apart from that, the way we have listened to music and watched movies in the past would also have been very different if we hadn't have lasers. And laser technology will also be very important for the technologies of the second quantum revolution. However, the laser as we know it today faces some limitations and is thus not suitable for all these applications. And one example is actually sensing. In sensing, many measurements and the sensitivity of many measurements is actually limited by quantum noise. What that means can be explained by that formula. So the sensitivity is actually given by the ratio of the signal to the noise, and the signal actually depends on the number of photons that are used in a measurement, and the noise depends on the square root of the very same number of photons. So from that formula, in a sense, you also see what you can do to actually improve the signal-to-noise ratio. And that is, you can either increase the laser power or increase the measurement time. Because that way, you get more photons. And as you see, the signal grows faster than the noise. And I guess you can all kind of relate to that situation when you think about train journeys and if you try to listen to music on a train. You really have some background noise, which is really annoying, for example, from the train or from people just talking, and that limits the signal-to-noise ratio of the music you are listening to. So you can't really enjoy your music to the fullest because the noise is disturbing it. And what you then do is actually you turn on the volume. You make it louder, so you get more signal, but in the end, it's probably too loud and you will hurt your ear. And it's exactly the same in laser technology. So as I said, you can increase the optical power, but that creates new problems. So for example, if you have very sensitive measurements, like measurements with biological probes, you might basically just destroy your probe and burn your sample. Or if you already have high powers, you might also misalign your measurement device because light is always absorbed in optics and the optics heats up, and thus some misalignment might occur due to that. So that's one of the problems. Maybe you also want to maintain an eye-safe environment. And then the optical power is naturally limited because too high powers are not safe for the eye anymore. And if you don't want to deal with laser safety measures, you don't want to increase the laser power to arbitrary levels. Could also be that high power lasers are basically just too costly or they don't exist at all. So that's also a limit that you might face. And there are actually many applications at the moment that are at that threshold and that face this limit. So one example is gravitational wave detection, which is a scientific application where the power is already quite high and cannot easily be increased anymore. But then there are also many examples from biology where people use lasers to analyze, for example, viruses, and where the laser cannot be increased in power anymore because you would just destroy the sample. So at this point, the question actually is, what else can be done to increase the sensitivity? And the answer to that question is basically use squeezed light. And I now want to explain why this works on a few slides. And to do that, I would like to explain you first what the light looks like that is emitted from a conventional laser. So here you basically see the distribution of photons coming out of a conventional laser. You see the probability to detect a certain number of photons in a given measurement interval. And you see indicated by the black arrows the standard deviation of that distribution, which is leading to the noise that you observe in the measurement. In this plot, I basically just shows an average number of 10,000 photons, which is basically related to the optical power of the laser. And if you now use a squeeze laser instead, you can see that you get a significantly smaller standard deviation. So you basically squeeze the noise, and by that way, you increase the signal-to-noise ratio in the measurement, but actually not by increasing the power, but by reducing the standard deviation and thus the noise. So you get a better signal-to-noise ratio by using squeezed light. And the way this works was also demonstrated in some experiments that we have done in our group. And these are shown here. So this is really an example where we basically measured the movement of a mirror that is shaking, and it's shaking at a frequency of 4.8 megahertz. And from left to right, you can see that the amplitude and the way it moves becomes smaller and smaller until at the end, nothing can be seen anymore. And that measurement was basically done with a conventional laser. After that, we added squeezed light, and you can see that the signal-to-noise ratio immediately increases because the noise goes down. So from 1.2 to 4.0 on the very left. But what's also interesting is here on the very right, the signal that was previously hidden in the noise can now be seen, and you can actually discover signals that would be invisible otherwise. So thinking back about the train journey, this is really like the noise-canceling headphone for sensing applications, because you basically reduce the noise, you get a better signal-to-noise ratio, and you can listen to your favorite music while maintaining a pleasant volume without running the danger of hurting your ears. And that's actually one of the main use cases of squeezed light, but there are others. And probably you are aware of the problem that computers that we use today are basically too slow to solve some complex problems like the optimization of ship routes. And to tackle that problem, people are working on quantum computers and are trying to build quantum computers. And there are many different platforms to realize quantum computers. There are also platforms based on optics and on lasers. And these platforms also require laser technology that is different from the conventional laser technology that we have. And here, squeezed light can actually also help to build optical quantum computers, which people already have done and where people already have demonstrated a quantum computational advantage. So you can see that squeezed light is really an important enabling technology for the second quantum revolution, and that's why we focus on building squeezed lasers at Neue Labs. Here you can see two devices that we've already built and that we've delivered to our partners, one at 1064 nanometers and one at 1550 nanometers. Both systems are powered with a conventional laser. In the 1064 case, this laser is a coherent Prometheus laser. And in the 1550 case, it's an NKT fiber laser. So these lasers are coupled to our devices here in the boxes, and then the boxes emit the squeezed light that is used in the applications. These boxes actually come with an integrated control electronic system. So all the electronics that you need to control these devices are packed in a 19-inch rack. And this can be really easily controlled by a graphical user interface, like just a touch screen, so that you can really focus on the application and doing work with squeezed light and don't have to deal with generating this kind of light. So the squeezed light is really the key product of our company, but we also provide the accessories that you need to work efficiently with their technologies. And that can be, for example, special detectors with high quantum efficiency, low electronic noise, such that you can really see tiny signals, mode filter cavity to optimize the laser beam in the application, but we are also open to doing complementary products and custom solutions for your project, because we know that every project is slightly different and might require different solutions. With that, I would like to thank you for your attention. So if you want to know more, please ask now or pass by our booth, which is just over there, or write me or call me anytime you want. Thank you very much.